Good morning, everyone. Today's webinar will be a tag team by Chuck Barnett, President of Dura-Bond Bearing Company, and Chuck Lynch, Technical Director for AERA, Engine Rebuilders Association. Chuck B will talk about advances in valve seat materials, their uses, and why OE have turned to them. Chuck L will give us the technical aspects of machining these very hard seats. Chuck Barnett is the owner and president of Dura-Bond Bearing Company, located in Carson City, Nevada. He is a Navy veteran serving during Vietnam in the VAP-61 Photo Reconnaissance Squadron and was deployed to 4 aircraft carriers in Guam, the Philippines, Australia, and Thailand. Upon his return to his native Seattle, he finished college at the Jesuit Seattle University with a degree in business and marketing. After graduation, he joined General Motors, AC Delco in Seattle, New York, and Los Angeles. He was later recruited to be General Sales Manager, North America, for PACCAR, Peterbilt Kenworth Trucks, in Seattle. In 1995, he was hired as president of Dura-Bond and moved to Carson City, where he has become the current owner. His hobbies include several vintage cars, fly fishing, traveling with the family, and spending time with his buddy, a golden doodle. You don't need me to tell you that powdered metal valve seats can be difficult to machine. In today's webinar, Chuck Barnett will go over the history of these seats, the composition, and how the recipe can be tweaked based on application. You'll learn why this material has become the material of choice for OEs. Chuck is now going to talk to us via a video.
Hello, I'm Chuck Barnett, the owner and president of Dura-Bond Bearings. Today, we thank you very much for joining us. We're going to talk a little bit about valve seats and the valve seats of importance going forward. Fortunately, Dura-Bond has been in business for 70 years, been making valve seats for 30 years, and the valve seats are a unique type of product that is really important for you for new technologies going forward. So with that, we're going to have a little presentation of the pieces of valve seats and that part, which I'm going to go through, and then we'll talk about some other things after the fact. And I think all of you know Chuck Lynch through his work at Jasper, AERA, and he's been a great stalwart person of the industry. So I can tell you a lot of things about valve seats, but at the end of the day, what I call the rubber meets the road, that's where we're going to have Chuck Lynch, and he's going to talk about some of the things about machining, which is the critical part of all this. So a little bit of the history again of powder metal valve seats. It's been around for a long time. Again, we've been making them for 30 years. It's pretty much a standard commodity in all OEs today. The beauty of the seats is it's not a product, it's a process. And that process of powder metal valve seats takes a whole lot of different types of materials put together in a cold form. They're compacted at 100 tons, and in that compacting process, the material stays the same throughout the whole process. So all the way around the valve seat and all through it is the same thing. The good thing about it, much like baking a cake, you can put all kinds of ingredients into the cake. You can put free graphites into this powder metal, which makes it better for machining. Tungsten's in it, we can put cobalt into it, we put all kinds of additives into it, which is a little harder to do on a cast type of product. So it's the future, has been for a long time. Powder metal is used in lots of things within cars, including the connecting rods and the new Corvettes. So it's a very strong material, very durable material, and one that's going to last. With the series that we have several series that we make. We make a 30,000 series, which is primarily for gasoline engines. We also make a 70,000 series. The 70,000 series is the same type of product, but it's made with oxides. Those oxides in there make it so it's good for heavy duty. It also makes it good for the LPG. Oxides makes it so that you can't micro weld a valve and a valve seat together. A great piece that no one else has. Beyond that, we go into a 90,000 series. A 90,000 series seat is similar to the 70, has oxides in it as well, has more tungsten in it, so it's going to make it a more robust seat as well. Beyond that, we've developed in the last few years the LS seats for the General Motors, Chrysler, and others, with the copper infiltrate. The copper infiltrate allows more heat dispersion out of the engine into the valve seat. And as you know, about 70% of the dispersion of the heat from the engine comes out of the valve seat. So this copper infiltrate that we put into it, it's about 15% that allows it to go out. This was designed by General Motors, particularly for their LS engine. The LS engine had a problem trying to get the heat out. This is a solution to be able to do it. Also works good in the Hemis and many other applications as well. So recently we've also done a new seat, which is called a Cobalt seat. The Cobalt is for some of the newer engines, particularly like the Power Stroke 6.4. Has a lot of cobalt in it because, again, a lot of heat in the engine. So we've got a whole range of different products available for the new technology. Is really important to go forward. Like many things, you talk about transition from drum brakes to disc brakes, carburetors to fuel injection. These types of technology changes are very important. Makes the cars a whole lot better than the have-been cars, trucks, and commercial vehicles. We currently have about 3,700 SKUs available for valve seats, which all those are made here in our plant in Carson City, Nevada, USA. All the materials are here. We have always done this on site. We do it by sizes. We do OD/ID depth. We're currently working on an online catalog that will hopefully be available towards the end of the year. And that'll have some other great features that we have on their cam bearings. So if you look at the cam bearings, and particularly cam bearings for the Chevy 350, we offer a whole range of cam bearing sizes. If you have a problem with a cam that needs to be addressed, or some oil pressure problems that may be in the engine, we have a whole lot of different things. And of course, all those ideas come from you. The same thing on the valve seats going forward. We'll have a standard seat, which is the factory seat, and we'll also have a number of different options of OD, ID, and depth. And so in our catalogs we have now, in our online search on the computer, on the website, we have a search option which does it by OD, ID, and depth. So that's a really important feature to have. This will be another feature on there when we have catalog applications as well. So again, with this in mind, we have a short video that you can look online to see. Gives a little tour of our plant, how the actual processes going forward, and how that goes about. So we think that this is a really important piece for you, a piece of continuing technology going forward, and we look forward to going forward with this with Chuck Lynch. Chuck Lynch is going to now explain a bit about the seats, machining, his experiences with different shops in the area, his experiences with people like Jasper, that we've done a lot of business with, and a lot of other ones besides. Thank you so much for spending the time with us with Dura-Bond. Thank you for all your support, all your good ideas that you've given us. You made the difference of what we do for the industry, and you're the heart of what we do and soul of everything that happens. So again, thank you so much for your time and interest.
Thank you, Chuck Barnett. We're now going to move on to Chuck Lynch. Chuck has been in the engine repair industry for over 30 years. His career has transitioned him from depot maintenance vehicle repair in the United States Marine Corps to production engine rebuilding, service equipment repair technician, sales engineer, and industry association support. 20 of those years, Chuck was working in the PER world, where he served in product quality, production support, and process engineering capabilities. Currently, Chuck is the Director of Technical Services for AERA. He leads the AERA team by developing new technical programs and services for AERA active members, along with enhancing AERA's custom training programs, international development, and more. We're now ready to tap into Chuck Lynch's vast knowledge of operations, equipment, and processes to understand what you need to do to get the results you need for a quality job for your customers. Now let's hear from Chuck Lynch of AERA.
All right, good day, everyone. All right, so let's get started with where it all begins, because I know there's several people probably listening today that we've had these conversations multiple times, and we chase after cylinder bore finishes and making cylinders absolutely perfect. We'll fight valve seats, and oftentimes it begins with a guide not being properly machined or prepared for doing valve seat machining. So on that, so you cannot produce accurate valve guide seats if you do not keep the guide processing under control. Can't speak to that enough. Super critical point of trying to get good valve seat machining. So if the reference point for the seat is subpar, the seat quality will suffer. The following points are some of the symptoms that you will treat if you do not address the root cause. So get into the guide types. We've got powder metal, which is the predominant material of choice in OE head castings now. So oftentimes we have to deal with the fact that they come in powdered metal, and we may not have that as an option. So when we replace a guide, we're going to be way off of alignment from where they were at the OE level. There's cast iron alloys, and then there's bronze alloys in solid, or in many instances, people will actually put a liner in a guide. The guide material can impact the amount of stem to guide clearance required, but it should not be considered when establishing your taper and outer round tolerances for the idea of the guide. So basically, your geometry allowances shouldn't be affected by your guide material choice. But again, it can impact what you choose for stem to guide clearances. This would be a typical guide ID and taper tolerance. So you'll see anywhere, based on whether we're using SAE or, a metric specification, but, you see 4 to 5 tenths maximum variation allowed in the guide. The further the seat is away from the guide, the greater the issue of taper within the guide. So, if you have that amount of taper, it's just going to aggravate your ability to, locate, say if you're using a seat and guide machine, or if you're grinding seats, it's going to aggravate your ability to locate on that guide. We speak often to tapered pilots, but that's not really the purpose of those. It's more about getting to secure the pilot in the guide. So seat issue, guide cause. So, random seat run out measurements, chatter, differing results if you regrind or recut a seat, poor or varying vacuum test results. So let's start at the top, random seat measurements or run out measurement. If you have guide sizes that are all over the place, and you're trying not to select multiple pilots, in a productivity sake, you can really chase locating. That said, it's probably going to be indicated in your seat run out, but if you're not measuring seat run out, you may have leakage issues that you chase. Chatter, again, it's about rigidity. So you want to have good straight guides, you want to have good pilot selection, and all of the things that you can do to make your setup extremely rigid will impact your finished seat results. Chatter, undulation, things that we'll talk about in some future slides. And here, if you go and cut the same seat multiple times or grind it, and you have, the high spot moves around, then, it's probably, there's a list of things that we could say that, are the problem, but you have to have a consistent, straight, true round guide to locate, to use the term repeatability and reproducibility, R&R. You know, you need repeatable and reproducible results, and you have to have a straight guide before you can make seats that'll yield that. So back to that, pilot selection should be indication of the quality of the guide. If you're using more than 2 pilots per application, unless you're using the half sizes. So as a rule, most of the pilots are 4/10 of a thou in separation from one pilot size to the next, but you can actually buy half sizes that are, you know, 2/10. The guide sizing is not controlled well if you're using, you know, 2 or you know, more than 2 pilots. If you think about that, that's about 8/10. Well, if my stem to get, or if my geometry is telling me plus or minus 4/10, then I really shouldn't be using any more than 2 pilots per engine family. If that's the case, then hey, go back and take a look and try to straighten up the guides. The pilot should be clean and free of debris when moving bore to bore, so the centering is not affected, or the guides could be damaged, you know, due to seized pilots. So typically you want to make sure that, you know, as you're moving from hole to hole, you know, if the opportunity presents itself, take a rag and wipe off any debris that would have clung to it. You are using lubrication a lot of times, so it's pretty common that you're going to have hard particles. As we talk about powder metal seats, some of those hard particles that we were discussing earlier, if you carry that into a guide bore and you spin that against a carbide pilot, you can do a lot of damage to a valve guide. So moving on to the valve seat, and I do want to mention, we had talked about this prior to the presentation. Feel free to interrupt at any time. That way we're, you know, thinking about that particular subject matter at that time. So if you do have any questions, please interrupt. So what is the purpose of the valve seat? Of course, number one, provide combustion seal. The very important part, as Chuck mentioned in his part of the presentation, transfer heat from the valve head into the casting and of course to the cooling system. And why do we have different seat angles? You know, so they tune airflow dynamics, primarily tumble and turbulence. Swirl is more controlled by piston and runner designs and so forth. But tumble and turbulence, which is very much needed in certain applications to help atomize fuel. So the valve seat can be instrumental into improving those characteristics. So the primary function of the valve seat being for combustion seal, the following points are important to ensure that function. So a common rule is valve seat run out or concentricity is less than 1/1000th per inch of seat diameter. But here's the caveat to that. As we look at engines today, we're seeing tighter and tighter stem to guide clearances. So if you have less stem to guide clearance, then you're going to need to allow less valve seat run out. If you have a seat or a valve that's 1.9 inches in diameter, and you have a guide that you're going to set up at 1/1000th stem to guide clearance, you know, the valve manufacturer has a tolerance on how much run out they can put on the valve as well. You are definitely going to have stem to guide contact, and that, you know, load is going to accelerate guide wear. So again, really think about what your stem to guide clearances are when you're setting your rules for valve seat run out. So valve seats are often cast alloys, but powder metal or PEM products are increasingly common. In automotive, they've been around for a long time, but now you're seeing them in heavy duty. You know, Chuck mentioned the Power Stroke diesel. In industrial applications, a lot of those were, you know, cast alloys. You know, they were stellite, real high nickel compositions or something. And you're seeing the PM products are in those applications, and they hold up very well. And, you know, as Chuck mentioned, you know, you can use materials that are non-weldable. So you don't have the micro welding and the seats being pulled apart. You know, years ago when the LP stuff, the conversion started to happen, you know, doing away with valve rotation, because you knew that you were going to have some micro welding as it tore that material from the valve seat. Then that would rotate, and then now that's the only area that's actually, you know, contacting. So you would have extreme leakage, and now I have this piece of material that's stuck to the valve, and it's working like a hammer. And, you know, so I've lost seat contact, heat conduction is lost, and now I've got this little tooth that goes around and picks the seat to pieces. So so it's nice to see that we've progressed with these compositions that they'll live in any of these environments. And, you know, I think everybody wants this. Had a conversation just this morning about, you know, seat selection. And there is no single seat that's correct for every application. I think we've tried and tried and tried. And the reality of it is, you know, the products, how these engines are engineered, the application that they're going to be applied to. It's just, we haven't got to the point where there's a seat that's correct for every application. So here we'll go over some of the rules on valve seat installation. Again, this is going to be recorded. You can go take a look at this. A lot of this information, you know, this particular graph is from Dura-Bond. This information is available with, you know, me on the tech line. You can give me a shout, or Dura-Bond will help you, or the seat and guide machine companies that we're going to mention can provide some of this information. So this is readily available information that you can access after this webinar. So when machining a cast iron head for valve seats, typically you do it dry, no lubrication necessary for cutting the counterbores. I know more and more people are using machining centers, and if they consistently set up and say, hey, I want to use coolant, then that's fine. There's no negative to it, but with the cast iron, you can definitely machine without using lubrication. Typical RPM range, you're going to be using carbide most often. You know, that's another issue that we'll cover, that we tend to overwork carbide. It doesn't like the super high surface footages that we tend to try to run with our seat guide machines. So sometimes we're our own worst enemy by, okay, I want to be more productive, so I try to run faster and I push the tools beyond, you know, their design limits. So when machining an aluminum head for valve seats, lubrication is definitely recommended. Typically inserts are different graded. Sometimes they have coating TIN, maybe they're even a PCD tipped insert or something of that nature. So 400 to 600 RPM, so significantly higher RPM. You want to maintain the insert edge, as aluminum tends to stick even with lubrication. So you probably need to look at the condition of your insert edges, maybe a lapping stone, something as simple as, you know, kind of a dull knife just to pick the material. But, you know, that's a pretty standard process you'll see in many shops, you know, when machining the aluminum.
Hey, Chuck.
Yes.
Can you go back to the 2 slides prior when you had the copper seat? We have Claude
Yes.
who's asking, can you explain the copper wafer? Is this on top, bottom, or sandwiched? And how is this machined to spec?
Okay, so actually this is one of the Dura-Bond advertisements that they use. So this copper wafer is in the manufacturing process. So when they get the near net seat, and then he was saying they were 15% typically copper infiltrate. So that will be put on the seat face surface, you know, as it would contact the valve in their manufacturing process. And then as it goes through the sintering, so that copper is actually going to leach into the seat and be pressed. So it's actually integrated. This is just basically an illustration showing that, hey, this is copper infiltrated seat. you know, I take a typical seat composition and then I add this copper. It's not going to look like that when you open the box. I hope that answered the question.
I think it does, Claude, but if it doesn't, let us know, please. Thanks, Chuck.
Sure. So methods of machining valve seats. By and large, I think most everyone has moved or migrated to you know, cutting valve seats, but there are many that are still grinding seats and effectively. It just takes patience, practice, and knowing what to look for. And you got to check a lot more, you know. So a form tool is always going to put the seat in the same place. If you're grinding, you have to make some adjustments. And again, you know, because you're creating a lot of abrasive, you got to really watch your tooling. So if you take a look at grinding, though, when I take this question about, hey, can I hone that Duramax with my vitrified abrasive because it's got those hard spots and cylinders? Well, think about this. What is the most precision process that we ever do? When something gets really, really precise, we grind. So if you look at honing with a vitrified abrasive in that Duramax application, okay, so I'm really just reverse grinding. It's very capable of doing that. And when it comes to grinding valve seats, hey, even though that it takes a lot of effort, in contrast to a seat guide machine, you can still do it. You can do it very effectively, and you can yield all of the parameters that you need to ensure a good seat face contact. So moving on here. When grinding valve seats, the following points can be right abrasive for the seat type. You know, I know there's a few different suppliers out there. You know, like with Goodson on the tech line, they'll have a lot of conversation with you about, you know, the seat materials and what you're trying to do. And, you know, they have people on staff that can help you make sure that you select the right abrasive for the seat if you're, you know, kind of new to this. Steel pilots, they can be quite the cost advantage, but they are easier to bend. The bad thing about carbide is it doesn't bend, it's going to snap on you, and they wear more quickly than carbide. So again, you can't reiterate this enough. You know, when you start chasing your tail, you know, we tend to not like the sticker price of some of the tooling that we have to replace. And well, this thing has served me well for, you know, it can't be the tooling because it's always been good. Well, it doesn't just wear out overnight. So you got to keep an eye on your tooling for damage and wear. And, you know, in simple things like orientation, you know, you always, you know, maybe if you are trying to get the max life out of something, then you need to keep a better idea of, okay, you know, which side do I always put to, say, 9 o'clock or something of that nature. So if you have, you know, random setup processes, then you can kind of, again, chase your tail because, you know, that's just more variables that you've thrown into your operation. Keep dresser diamond maintained and chip free. You know, if you get too aggressive, hey, I really wore that stone out on a tough seat, so I know I'm gonna have to take a good amount of material. So I go at dressing that grinding wheel pretty aggressively, and then I build up a bunch of heat, and that's what will take out that diamond. You know, is, you know, you'll get a heat sink, and then they'll get a crack in them. Of course, you could damage them from impact or something, but you want to spark out, but don't dress too smooth. So if you have an abrasive that is loaded, or it will not cut. Likewise, if you spark out or don't spark out, or you dress too smooth, you have some of the same characteristics. So it acts just like the, you know, it's a loaded up wheel and doesn't cut well. Don't dress too coarse, because whatever pattern you created from your dressing process, you're just going to transfer back into the seat. That's also true of grinding wheels for like cranks or camshafts or something. So, you know, you got to find that sweet spot. So seat and guide machines, I've kind of listed, the most popular ones that are out there and being used today, and members of the group that we work with every day. So you see from Rottler, Comec, Robbins Machines, Surdy, Newen. So seat surface. I borrowed this slide here from Newen. I actually like this. It gives us a good illustration of what happens sometimes when we're cutting valve seats. So a desired surface is without chatter and undulation. This is true of both the valve and the seat. Typically, you're going to look for a roughness of 30 RA or less. That'll be called out on most of your drawings. Measuring valve seat surface finish is pretty tough. Some of the PERs do actually measure that, but the average guy to go out and buy the fixture that'll hold his profilometer to measure valve seat roughness it's just not commonly done. But there are parameters around valve seat roughness. And then the seat width is based on the application. You're not going to run an intake seat width as wide as you do the exhaust. Why is that? Because the more contact area, the greater the heat sink, so I can dissipate more heat. So with the seat and guide machines with steering wheels, feed rate cannot always be controlled accurately. That said, the seat diameter and tooling grade will still control the desired RPM. So this chart illustrates suggested speeds for carbide form tools. You can take a look there, seat OD and RPM range, and then you look at some cutting angles, relief angles. If you take a look, Surdy's got some unique tooling now. They got their more rigid, heavy-duty stuff. Robin Cheerer with Robbins Machines, he's actually been working on some of the Ruby material as of late. So that's something that we're constantly working on in the industry to try to improve longevity, so that you don't have to sharpen so much, because that is an area where we start to create issues is with our sharpening processes. That some places have it really nailed down because they have very specific equipment, and then some shops, it's more of a manual operation, so it does lend itself to some potential inaccuracy and great amount of variability.
Chuck, you have another couple questions here. Chevy is asking, how do I deal with tool deflection on powder metal seats? Pilot deflection? So that's kind of a combined question.
Okay, so the tool deflection is oftentimes, about the overextending of the insert holder relative the tool holder. So you want to keep, and I got another slide about this coming up, you want to keep the head as close to the cylinder head. You want to keep as close to the work head as possible. And then you want to keep so anybody that's using a seat and guide machine, they know, say a 2002 insert holder, a 2001. Well, if you're extending a 2001 to its max dimension to cut a particular seat diameter, then you're going to have more opportunity for deflection. Again, the more rigid or robust you can keep your insert and tool holder combination for a particular diameter, you're going to see improvement. Another challenge that you have, like a pilot deflection, if you're using a steel pilot, and if you're grinding a seat, it may be that you have to do a multi-step process, because you are going to be, if you have a high eccentricity issue with a valve seat, say I replaced a guide, or there's a lot of material in the throat that I want to remove. So you're probably going to have to do a roughing pass and a finishing pass. And that's true of form tools as well. You know, sometimes you have situations where someone will go in with just a single angled cutter and cut the throat at 60 degrees so that it doesn't influence their seat angle and top angle so much. Again, you add cycle time, but you know, if you address some of those issues and you're not chasing that at your final assembly, okay, now I have a leak and then I got to go back, you know, so maybe a little more time spent in the beginning can save you some time in the end. So I hope that answered that.
I think so, Chuck, but if not, let us know. Okay, we have another question from Donald. Can you discuss form tool contact area and the relationship of that and controlling chatter? He has a SERDI 100 machine.
Okay, so a lot of the insert profiles that we'll look in, you know, in a catalog, and we'll go with, you know, okay, so I know a 15 on the top will cover any and everything, and then I'll do 45 on the seat angle and 60 in the throat. So if you can reduce those to, you know, say a 30 in the top, 45 on the seat, and 52 in the throat, because a lot of times, especially if you're cutting a seat that's pre-existing, then all the profile is really there. So take out as much deflection as you can by reducing angles. Again, when it comes to special relief angles and rake angles of the cutting tool, then you really need to talk to your machine supplier, because it does vary between, you know, Rottler and Berkrow and Sonnen and you know, New and what, you know, Robbins has available now. They've just recently released some new products. So you might talk specifically about an application and try some of that. But the biggest thing you could do is reduce the amount of total contact you have, and that'll improve, you know, all of the things from run out to chatter, undulation, you know, because, you know, it's pressure. You know, if you take a look, you may be cutting 300 thousandths of contact surface area, you know, so that's a lot of load. You know, that's, if you're boring a cylinder, you never see that kind of load. You're working from a 30-second nose radius or something of that nature. So we're expecting a lot of the tooling.
And Chevy says, good, that answers his questions. Thank you.
All right, good deal. All right, so some CNC machines are designed to generate a seat profile using the single point insert, and that may be carbide, Cermet, CBN, etc. So if you take a look there, you're going to run significantly higher RPMs. Again, so you're using a super abrasive typically, and I say that typically you're using super abrasives in these type of machines. So you can see some much higher RPM, and then the feed rate you can definitely control. So if you see that rough feed rate of you know, 4 to 5 thou, think about that when you're using just a carbide on a machine with a steering wheel and you have an insert profile that engages at 300 thousandths. This particular insert, in most instances, it's got a 16 thousandths nose radius, which means that you're probably only really contacting at 4 to 5 thousandths. They actually have some profiles where you would machine on the bottom edge of the insert for your roughing, and then you travel like from the inside diameter to the outside diameter, so that you're actually using the opposite edge of the insert for the finishing process. So it almost is like you have 2 separate cutting surfaces, and it's only cutting at about 5 thousandths material as opposed to, again, 300 to 400 thou. So that's just, you know, that's some of the technologies out there today. You know, you got the new one, SERDI's got the Stronach. I definitely wanted to cover those. You know, do see more and more of those machines out there. So as cylinder heads have evolved, so is the need for tooling. Some of the challenges are, of course, hard material, small stem diameters, challenging seat profiles. Sometimes I think we don't think about, especially if we're a custom shop. It's something we actually added to process. Is okay, man, how many valve seats per combustion chamber? Because I don't just look at that as an inline 4-cylinder anymore. What if it's a Volkswagen and it's got 5 valves per chamber? It's a lot of seat cutting. So I'm asking my tools to do a lot more, and then head castings that are odd shapes and are hard to secure in the machine. So going back to what I was saying earlier, with say if you run a live pilot machine in the tool holders, anytime you put a pilot in a tool holder that has a set screw that pushes it off to one side, it's hypercritical that you know the condition of the bore that you're putting your pilot in, because I'm starting with an eccentric, and everybody knows what a fuel pump eccentric is and how that cycles. So if I have a pilot that's worn on the top and I have a body that's got wear in the ID, and then I have a set screw that pushes it away from the set screw. So now when I start that tool in the spindle, which I also need to look and make sure that I don't have run out between the spindle and the tool, I can really aggravate things. So if I go into that guide bore and I put an eccentric in there to start with, and then I don't have the head clamped well, it's going to try to push the head around with a pilot. So then you can get extreme cases of, chatter and undulation and things of that nature. So again, it keeps going back to, you got to know your tools and maintain them. So performance, poor sharpening can produce poor seat quality. The toughness of the material, there are seat alloys out there that have a lot of nickel in them, and much like the aluminum that we were discussing earlier, that's a tough, stringy material, and what's it do? It bonds itself to that insert, but that tough, stringy material also is micro welding to the seat, and then you drag these chips in there, and as it welds itself to the seat, you leave these channels in the seat. Now, what really happens is you're only setting up, or when the valve is contacting it, you're only contacting the highest points. So again, do you need to have a secondary operation where you go grind, lap, recut, single angle cut, so all things that you need to consider. Again, use the most rigid tooling available based on your application. Sometimes you got a seat material that's beyond your application need. So consider that too. Hey, if it's an intake seat, I'm going to use, Dura-Bond for their part numbers. So if it starts with a 3 or 30,000 seat material, they're going to work in a lot of intake applications. Sometimes you try to keep things simple and say, I want a seat that'll live in nearly every environment, so I'm just only going to buy 70,000 series or a 90,000 series, but really evaluate what your true needs are, and and that'll help you out with the cost of the tooling and having to have the most absolute rigid stuff. But by and large, always err to the side of caution and be as rigid as you possibly can. As we mentioned in the earlier slide, the distance between the spindle and the parallel bars, keep that to a minimum. I know you need to be able to move guide bore to guide bore. You have heads that are going to be tilted at odd angles sometimes, your Hemi, big block Chevys, anything that's played valve train. Sometimes you're moving that stuff 3 times. So, hey, the more clearance I could give myself, it'd be easier. But again, easier in one area may be more struggles downstream. So just keep that in mind. Again, do not extend tool holders to their max radius dimension and expect ideal results. Got deflection, and when you have deflection, ultimately you're going to end up with chatter. Some materials, again, they act stringy and they need a secondary processing. So form tooling maintenance. So tool bodies, you have ID wear, you have OD. So this is where the tool holder, the major body of the tool holder, would go up into the spindle. So you could get handling damage. So if you, for every action, there's a reaction. If I hit that metal, beside where I hit it, there's going to be two areas that raised material. And then I put that up into the inner spindle, and out at the tip of where the pilot is actually engaged in a guide, how much tilt is that causing? And then if I turn it 180 degrees, I probably get a different result. So, be aware of those type of things. Pilots tend to wear more, in the guide region. The insert pocket holder can lose angle. I've been fortunate enough to be able to use like an optical comparator and say, okay, this is going to be the gauge fixture or insert holder that I have to set a standard. And then I can take that same insert, put it in a different one, put it on the block, put it in the comparator, and find out, wow, I'm a full degree from where I should be, because again, you're applying a lot of load. So the area right out at the extreme edge, under where the adjuster screw is, and the screw that retains the actual insert, you can kind of break that material out, and then the insert wants to roll on you. Poor sharpening can upset the cutter geometry. So what's pretty typical that happens with these grinders that are mounted to the side of the seat and guide machines is that, well, that wheel is pretty expensive, and then people go and they grind fairly aggressively. So it starts to get a rounded over shape on that grinding wheel. And so as we're grinding the insert, and then we roll off of it, as we pull the insert back from the grinding wheel, and so you roll over the edges, and now maybe I started with a 0 rake, and now I have 5 degrees positive rake, or I go to a negative rake because I'm trying to compensate for that. So there's just a lot of issues that can show up from sharpening. And then so live pilots can also gall. Sometimes they'll gall inside of the tool holder, or they'll spin in the tool holder and you'll transfer the steel from the tool holder onto the pilot. But more often than not, they hang up in a guide, and then they get, they're stuck. There's damage in the operating range. Well, if you try to hone that off or polish it off with a crankshaft belt polisher or something of that nature, you can really mess up the geometry of the pilot. I know the things are extremely expensive, so again, that's even more reason to make sure that we control our guide sizing, make sure that we, wipe down the pilots, that we're clean, we're lubricated, and we don't set ourselves up for those type of issues. Valve to seat contact. So this is one that, a lot of people that are new into the industry will get confused with. Okay, what is upper line contact or bottom line contact? So typically when you'll hear that term bottom line contact, it means closer to the stem diameter. So if you're hitting closer to the stem diameter first when you're checking your valve seat contact, that's not good. If you have any difference angle, like this slide, you want your difference angle to be indicated, where it's hitting out closer to the outside diameter of the valve. So I see you on social media sites and stuff, why no interference angle is ideal. In a perfect world, it would be. And some of the valve design engineers and so forth will tell you, even if you have interference angle, you're ultimately going to end up with full face contact. But So if we, in a static state, it's impractical because, okay, the valve manufacturer's got a tolerance, plus or minus 15 minutes or a quarter of a degree, unless you order something special, and then you're probably not going to want to pay for something that has zero tolerance on the angle. And then there's always going to be a fight. Well, you know, at the factory, I know my stuff is perfect at 45 degrees, and how do you test it when it comes in? So, you know, there's always that argument. But again, you're going to have a tolerance for the valve. The form tool cutter, the same thing. So they're typically going to manufacture an insert that's got plus or minus 15 minutes or a quarter of a degree tolerance on that cutter. And then you take a look at combustion forces, depending on head diameter, material, does it have a compression button in the valve already? So, you know, low RPM, high RPM, under load, unloaded, you know, so you're going to get valve head deflection. And then both the valve and seat, you know, must have better geometry with no interference angle. So if you're starting from the word go and you try to make it a zero interference, then you better really have your ball game together. So here's some kind of the, you know, the examples of okay, what a good seat contact would look like. And this is the one to the right would definitely be something where the valve is hitting the seat. It's not locating well, so it's pushing to the opposite side. And we know that that's definitely going to impact the guide as well. So bad thing is what happened first? Did I have a bad guide that put me in that position, or did I have, you know, poor seat geometry that caused that and wore out the guide? So why does this matter? Dispersion of heat. If heat is not transferred from the valve head to the seat, the heat stays in the valve head stem and then ultimately goes out through the guide. The guide clearances are not calculated for such a large amount of thermal expansion. You know, if you take a look at the hot rod diesel world, you know, a lot of guys, you know, Wagler competition and Fleece or Freedom Racing engines and Scheid and so. And I've talked to some, and they run crazy stem to guide clearances because they know that this is going to happen. Well, it wouldn't work on this. You can't start with 7 thousandths on the street in, you know, an automotive diesel world. You'd have huge amounts of oil consumption. And again, the seat or the valve needs a good datum point. So, you know, those things are running on the ragged edge for a shorter period of time. You know, if we want something that's going to last a long time, we need that location, that guide, that datum has to be accurate so that we hit the seat the same time or the same place every time. Valve stems are not designed to carry a lot of thermal load, and hence that's why from the mid stem weld to the valve tip is typically a lower alloy. It serves multiple functions. Okay, so most of your stainless type materials, your high alloy materials, you know, 21-4N, you know, Inconel, Nimonic, things of that nature, high nickel alloys, they don't heat treat well. So the keeper groove area, if you remember the old valves used to, they always had a hardened tip welded, you know, a wafer welded to the tip of the valve for the rocker to strike. But when you would try to pull the keepers and the retainer off, they would be stuck in the valve pretty well. And then the valve was all chewed up in the keeper groove area because it's a non-hardenable alloy. But these high carbon steels can't stand up to that nasty environment of the combustion chamber as well, but they do work well for the keeper groove area and the tip. So once you have too much heat escaping the combustion chamber area and going up the guide, then now you're really testing a material that wasn't designed to be in that environment.
Chuck, couple questions here. From David, can you advise which knife angle is best suited for a carbide seat cutting insert by the seat material you were cutting?
I think I would rather have some further discussion about, give me a call on the tech line. Let's talk about the application and the setup. Um, Again, because sometimes just a generic rule doesn't answer that, right? Um, so that would be my preference. I'd like to have some more detail about the particular applications.
Okay.
Again, rigid, like say, Surdy's got their thought, and some of the things that Robin's been working on, I think we should definitely talk about the particular applications. And it's all been driven from this issue, right?
Fair enough. Okay, Chevy's asking, why is bottom line contact bad?
So your ability to get rid of that heat, so heat runs to, if you take a piece of steel and like an axe head or something like that, and you put heat to it, heat always runs to the thinnest zone, and then it overheats. So I have a situation where the valve head diameter is hanging out there, and that area is getting extremely hot. Since it can't transfer the heat to the seat, or there's more distance where that thin area is being exposed and it gets really hot, then you have pre-ignition detonation type situations, and you can get burned valves. Sometimes you see like the bird beaks where the valves will overheat and they'll get little cracks that want to form in the outside edge perimeter of the valve. So that's kind of what's going on there.
And Chevy says, thank you. That's excellent.
Right, thanks. All right, test your work. So here are these illustrations, concentricity gauges and vacuum testing. So concentricity gauges, they vary quite a bit in what's available. My advice, highest resolution possible so you can see your work. And then, vacuum testing, a lot of folks are like, yeah, I don't need to check concentricity, I vacuum test. I will contend, and I'll argue this to the ends of the world, one without the other is not great, because concentricity can tell you what your machine's doing. You can check that R&R, that reproducibility, that repeatability. Say if I'm cutting my seats and I take a marker and I mark the high point that was left while I'm cutting the seat. If it's always at 2 o'clock, okay, I probably need to adjust something on my machine. But if it's random, I either need to adjust me, I need to adjust tooling, I'm inconsistent in my process. Again, I'm kind of one of those guys, kind of a gorilla, I need a torque wrench and I need a concentricity gauge to say, okay, your process is uniform, your machine's uniform, because, probably a little too much torque elbow. So again, use those tools. So I got a little way out of sync there, but why vacuum testing and measuring should both be performed. Run out's a good way to check your machine. Run out may not catch chatter and undulation. Vacuum will not catch excessive run out if the guide clearance is large enough or the valve head is flexing. 25 inches of vacuum will collapse a steel oil drum. I say, ask me how I know. I said this at a presentation one time. Somebody happened to go and try it because they didn't believe it, and that happened before I ever left the facility. So, in fact, it will happen. And then, so if you don't think that won't deflect a small block Chevy intake valve, you're greatly mistaken. And then run out. So if I'm measuring valve seat run out, you're not going to capture the little nicks or debris or something that'll cause you a leak. The bad thing about debris is first time the valve opens and closes doesn't necessarily mean that it's going to go away. Oftentimes it does, but if we're hard particles that we create from machining powder metal, If that's stuck around the seat somewhere and gets between the valve and the seat, didn't get washed out, and then now that material that's much harder than the valve may embed itself into the valve face. Now, again, it goes back to like that micro welding I'm talking about with the LP applications. Now I've got this hard little particle that's going to rotate around and hammer on the valve seat, and the valve face is going to fail. So again, point of cause, what was root cause in this instance? Well, now you're probably not going to know, but vacuum testing, if I'd pay attention to both of these, I could probably have taken care of that prior. And then guide size and geometry can make measuring run out difficult because of pilot selection and poor alignment. So if I measure valve seat run out, turn the pilot 90 degrees, 180 degrees, and I get a completely different result, then you start looking at your tooling and your setup. If you don't change it, you just pull it out, you put it right back in, and you got a different result. It's again, you're chasing your tail. So test your work. Some of valve seat wear factors, compatibility of the valve seat or the valve face and the seat material. A good example, so in 2011, when the Ford Coyote engine was, that platform started going into trucks, you see some of those come in, the intake valve, you could shave with, it's beaten in so bad, but the seat looks perfect. Some of the other factors are friction between the valve and the seat. So that friction increases with combustion pressure increase, thermal distortion increase, as seating velocity increases. In the performance world, we typically want to accelerate that to eliminate some of the scavenging effects one to the other. Again, so we try to move the valve back to the seat very quick, and for the duty cycle. And then friction between the valve and the seat decreases with lubrication and protective oxides. So mentioned a couple of times CNG or LP applications, and that was always kind of the story there. Hey, I'm using a dry fuel. That's really hurt me on valve seat longevity, valve train longevity, because there's no lubrication coming via the fuel. Seen a little bit of a similar instance with the direct injected engines as well. Not only do you have the issue with you don't have a cool charge of fuel passing the valve, you also don't have it washing the oil that accumulates in the combustion or in the port and comes in contact with the backside of the valve.
Chuck, Donald has a question. Please explain pitting on a seat or on the valves.
So the pitting, again, can often be like the oxide, so it's a corrosion in more instances than not. So actually in here you see corrosive wear, but pitting is often corrosion. So something nasty in the environment of the combustion event. Is it fuel? Is it created by the timing process, so the burn's not efficient? Is it ingesting coolant? Are you in, the quality of the fuel in your area? But more often than not, the pitting is corrosion. So moving on into the valve seat wear factors, you have adhesive wear, so that's the micro welding. Abrasive wear, which is most common, so that's your alignment, misalignment of valve to seat. Surface roughness, pressure from combustion, closing energy / velocity, and then corrosive wear. Hope that answered it. That was pretty good timing for the question.
Very good, Donald. Thank you, Chuck.
All right. So adhesive wear, so the micro welding, again, with if you take a look at, do I have the right seat material for that valve material? So now I'm battling micro welding. So this is just kind of a blown up view. You can tell you have some nice flat surface area, and then you have just areas that's pulled out. So due to localized bonding between contact and solid surfaces. Again, just reiterating, poor lubrication, high stress, wide hardness differential between the valve and the seat, surface roughness, which increases friction, and could be heavy duty cycle without break-in. The thing about break-in in the world today, we've talked about this in piston rings for a long time, is that we've migrated to materials and bore finishes and stuff that, rings don't really break in like they used to. And that's what's happened with valve trains too. You really have to have your valve seating right from the word go, because valves and seats don't just wear and match one another like they used to. You might change surface finish, but if you have concentricity issues, it's probably going to propagate itself into, guide wear or the valve failure. So valve seat wear prevention. So valve geometry considerations would reduce valve seat angle common in CNG and LP. Is that practical? Typically not. Then you have to design the cam for it and so forth. Diesels used to have reduced angles because if they weren't turbocharged, if you take a look at that cross-sectional area, if we got a 15-degree valve seat, a 30-degree valve seat, 45-degree valve seat, that cross-sectional area is going to be greater with that 15-degree valve seat. So they're trying to take advantage of the lift and the reduced restriction of the area, when you got a 15-degree valve. Another thing you can do to help the valve is increase the valve head thickness. But that adds, weight and cost, and then it's harder to do a compression. But you see a lot of the gas engines look at like the modular Ford 4654, 68 V10, the margin area of the valve is extremely heavy, so that they, get away from what I was talking about earlier, where heat runs to those fine lines, thin areas. So reduce valve head diameter. You take a look at, 2 1-inch valves in a combustion chamber. So I got 2 1-inch intake valves or 1 2-inch. You still can flow more air through the area over those 2 1-inch valves. So I can reduce that head diameter. I can reduce weight and closing energy. And then where you can, the performance world, you don't see this much, but again, they're not looking for longevity. But if you can increase the valve seat width, so it gives you more opportunity to dissipate heat.
Chuck got some questions for you. Daniel's asking, what do products like Seafoam do to the valves and seats?
To find a really, really defined answer for that, they may be inert for a particular composition of seat, and then another seat composition may not like it, especially once you mix it with the fuel. So we know that just driving around the country that we can have various grades of ethanol. So how does that react to fuel in Illinois as opposed to, Nebraska or the Dakotas or something? But again, because each state regulates that differently. So it may or may not be an issue. More often than not, those materials have been tougher on gasketing. The vehicle controls. They recognize pre-ignition detonation things better than they did before. But by and large, when they've missed the mark, like in the 5-liter Ford, at the OE level, they probably tried to cut cost out of the valve. And, so having them, they missed the mark on the matching the materials. I don't know that a huge change in the, or a small change like that in the fuel quality would have made much difference.
Okay, from Hayen. Is the micrograph taken after corrosion products are cleaned?
Yes. Yeah, that was a cross-section amount.
Okay, and from Rich. How do you feel about cutting beryllium? We have cut out own tooling to scrape rather than cut.
If you can create dust, you need some way to wash that down. So if you're creating dust, it's kind of a bad deal. For the sake of everyone's health and stuff like that, I mean, I'm going to default to, it's probably best to put it in a machine where you can have it being hosed down with coolant while you're trying to machine it. Because at what level does the dust become a concern? Anything you can, smell or inhale, I would be fearful of. I know a lot of people do it. I just, as a disclaimer, and I'm not going to advise that you do it if you can't flood it with coolant.
Thank you. That's it.
All right. So valve seat wear prevention, valve train design considerations, increase valve train rigidity, reduce weight. So some of the things in rigidity that you've seen go away over time and then come back, say like spring dampers. The length of the guide. You want to give a valve as much guide length as you possibly can to control the valve and be that, that good datum so the valve hits the seat the same every time. Of course, seat materials and so forth. Valve train weight, we've chased forever and ever. I think that's why you see so many engines have gone back to solid buckets. Reduce valve seating velocity, how to, reduce lash, cam lobe profiles that to make sure the valve is not being snapped against the seat with such energy. Again, it's a fine line you're trying to do. I want to take as much advantage of that combustion or that pressure making event as possible. But I don't want closing velocity to beat my valves and seats to death. So, everything's always a compromise. I always said it was amazing that, an engine that's constantly trying to blow itself apart every cycle, everything is like for every positive action, there's some kind of negative action that you're countering, so that's always the considerations. So whoever's designing the cam profile, that's what he has to fight. So in summary, guide sizing is extremely critical to successful seat machining. Stem to guide clearance is an important factor of valve seat runout tolerance. Correct seat material for application will still fail if the machining process does not yield accurate runout, geometry, and contact. So I'd like to say thank you to our friends at Goodson, Comec, Newen, Robbins, Rottler, Surdy. Everybody has given me some, freedom to use publication information, pictures, and so forth. And, I've made friends with many of you listening today and these suppliers over my career. And, couldn't be able to share anything of this information with you if I didn't have them as support. So, thanks. I want to thank you for your time And guess we'll open it up to any additional questions.
And we have a few questions, Chuck. Thank you. From Donald. It is difficult to find inserts that match fixed cutter ODs. Is there material available in bulk so we can machine our own? That's an interesting question.
Okay, so counterbores for seat pockets, I assume?
That's what I assume. Yeah, yes, Donald says yes.
I have to get back with you on that. The answer is roughly yes. I haven't investigated that for some time, but yes, you can buy, you know, the carbide in blanks that would be close to near net that you want. And then, you know, many of the guys out here are used to a line boring and have some of the old boring or sharpening fixtures, could produce some geometries that they want for, you know, making whatever they want. So again, give me a shout out on the tech line or something, and we'll see what we can do.
Okay, from Brad. What causes undulation?
So it's funny, I had this conversation just this morning about, okay, so you have chatter, so they can be a high frequency. Usually it's a, you know, it can be extremely high frequency. But, you know, if you're looking at like orders of geometry, you can have kind of like, though, you can hone a triangle, you can hone a square, you can hone a clover leaf, and you can cut valve seats the same. So as you set up that frequency, so as the tool lifts off of the valve seat, based on velocity, say it may hit at 110 degrees separation. You know, you could have pilot to guide clearance. There's a lot of things that will allow you to set up that frequency. Is the head moving? So am I reacting against the head's traveling one direction? The cutter velocity is so high that it's changed places. So kind of like an imbalance. And so you'll see seats that have 3 high spots. Pretty common with valve grinders too. You know, you'll get valves. This thing only has like 3 or 4 tenths run out, but it leaks terribly when I vacuum test. So if you put some Dicam or something or layout material, and you'll see that 120 degrees apart, you have you know, high spots, and that's kind of what undulation is. So it's not that real high frequency chatter that you will see often. It's, you know, some of the same setups will create it.
Well, I guess the question would be, can you comment on seat materials selection?
Yeah, so, you know, in speaking to the slide where I said that not every seat, or no, there's not one seat for every application. But if you take a look, just generally speaking, so, you know, with what Dura-Bond has, the 30,000 series is going to be a ton of applications that, you know, naturally aspirated. If you want to start going to like turbocharged, the diesel stuff, because diesel's, you know, nasty corrosive stuff, there's 70,000 series. I actually worked on some of the early 90,000 series that was in a high compression natural gas application, you know, and where we were using big heavy valves. It was a 429 Ford Stellite one in the intake face and the exhaust. So the intake valve, again, a high compression engine, big cross-sectional surface area of the valve. And so, you know, you're really pushing a big heavy valve into the seat. So the 90,000 series, you actually had tougher materials in the intake than the exhaust, which is totally goes up against what we normally do. So that's kind of speaking to, you know, some of the powdered metal products. I've seen some really great successes out of the copper infiltrated seats. If you can take the heat away quicker, it's going to make the work for the valve, you know, much improved. So if that heat sink is greatly improved, and everybody knows how well copper conducts heat, on almost to a default sometimes for itself. But anyway, that's a good option. And then of course, the cast alloys, you can kind of make up your own recipes there as well. But the application is really going to dictate your choice of seat. Is it highly corrosive? If it's just standard, automotive type stuff, used to, that was pretty easy. But now you look at how many engines are 13-to-1 compression ratio, direct injected. So those will steer you down a different path possibly. I think Randy Neal uses this all the time. He said it at the PERA meeting a couple of years ago. How many of you are building high performance engines? And most of the PERs are like, no, we don't. Take a look at how complex the engines are today. If you don't think EcoBoost is high performance, then take a look at what we used to call high performance, only 20 years ago. So the complexities are high performance. I know I got a little bit off on a tangent there, but like I say, it's just hard to say what seat necessarily will fit without knowing the application anymore. Today, more so than ever.
All right, next question from Jim. What are good seat materials for titanium valves?
So that would be a good opportunity to use something like that, a copper infiltrated. So titanium is going to be a extremely high nickel alloy, has kind of some of that stringy. It'll exchange itself with the part that it's coming in contact with. So you don't want excessively hard material for the titanium valves. And I know from talking with like the top fuel guys, that's why they actually still use a seat material, so they don't have the bounce and stick to it. On like the intake side, they'll use they're still using like ductile iron materials. But yeah, the titanium, if you run it against a super hard material, then your valve life is going to suffer. If you're on a pro team that changes stuff out really quick, you may not care so much.
Comment from Fernando. Thank you, Chuck. Great data. My best regards from Argentina. Thank you for your support from Argentina, Fernando. Donald is asking, I get seats that cut with squeal. I add pressure and they test fine and look fine, long solid chips. Is this the proper way to cut these? Do you recommend something like mist lubrication to preserve cutter life in high pressure? Is a long one, I'm sorry. I have to scroll on this. Do you recommend something like mist lubrication to preserve cutter life in high pressure applications such as this?
So those seats probably have a lot of chrome, and anytime you can put a mist at that when you're cutting, again, it's not real common that people will mist valve seats when they're cutting, but it needs to be a constant mist because you're taking advantage of taking some heat away. So if you give it a little squirt and you cut and then you get another little squirt, you may be shocking it because the thermal load is really, really out of control. But if you can put a consistent mist, yeah, you're definitely going to take some heat out of it, and that will help the tool life. And if you overheat the seat material or have a lot of variation in the heat of the seat material when you're cutting it, you may see some hard spots. Kind of like crankshaft grinder, if you're grinding a pin or a cam journal or something, when you see stuff start to go brown, and then you got coolant that hits it, and then you shock it. So sometimes you see in thrust well seed cracks or cam lobe, you see seed cracks. You could do some of those same things if you're being really aggressive on seat cutting, and then you were to blast it with spray a little mist on it. So like I say, my advice would be consistent mist.
So Chuck, it's Chuck Burnett, Dura-Bond. Just a comment as well. One thing with the powder metal seats, all those come off and it's a small chip, no stringy. And the strings that you see that Chuck has talked about a number of times are detrimental. But again, a powder metal seat in general comes off in just a fine chip. And that's something that's a particular advantage, I think, for the machining process.
Yeah, heats leave with chips, you know. So no matter if you're cutting a valve seat or you have something on a lathe or whatever, if you look at molded inserts for tooling, they've gone to, they call them chip breakers when they mold the surmet in design. So if I can make a chip, the heat leaves with it. But if I'm just kind of pushing that material and it's hanging on, then I'm retaining the heat, right, Chuck?
Correct. That's right. So that's a big advantage of having just a fine chip. And as you mentioned, you certainly want to wash it away, but you get away from the typical long, stringy chip that you get by a powder metal seat.
Okay. Next question from Ron. With the hardness of today's valve and seat materials and the lack of break-in, where be justification for not using an interference angle?
To go back to that though, again, what's the practicality that you can achieve a non-interference angle? You need to check every valve against every seat as you do that seat. I hear you. I know exactly where you're coming from, but in all practicality, can you achieve it? If you can achieve it and you can charge for it, then do it. But I think in most instances, you're not going to have a guy who's going to say, I'm going to have this valve, I'm going to match it to this seat, and then I'm going to do that on the next seat, and the next seat, and the next seat. So again, so I even said that in practicality on that slide. So in a perfect world, it'd be great, wonderful. But you don't know what ultimate cylinder pressure is going to be. That valve head design, if you don't have the analysis as to what the deflection is going to be at what cylinder pressure and at what temperature, it's a gamble.
Okay, from Ernie. What is your advice for using a 60-degree seat angle?
So if that was actually the contact angle, you would have extremely high wedge pressure. You could probably seal about anything. Probably wouldn't last long. Think of it as like anybody that's used a Morse taper, in a drill or something. You know how the taper, it's got a little bit of a drive lug for the rotational so it doesn't spin, but that Morse taper tool will stay in a spindle because of the wedge pressure of that angle. So again, it would probably wear itself out pretty quick, but it would seal tight for a while.
Okay, he's also asking, could you recommend any materials for using a 60-degree angle?
Valve, that would be tough. There are some ceramic seat materials that would function in that environment, but finding a valve material, because you can't run a ceramic valve in a ceramic seat.
Okay, a lot of great comments on the presentation. I'm not going to read all of them. Chuck will get these when we send him the follow-up on this. So thank you, everybody, for that.
So Joe?
Yes,
again, Barnett for a moment. I just want to thank Chuck Lynch, AERA, PERA, and all of you. The ideas that we get to make product comes again from all of you that are listening in. We appreciate it very much. And the association with AERA and Chuck Lynch, we've known forever. And with Joe Polich, who's put all this together for PERA, for the webinars, is fantastic.
And so hopefully, as I said in the beginning, we can tell you all kinds of things about product, but when the rubber meets the road, as we say with Chuck Lynch and others that have helped us either on the phone or this type of thing, means everything, I think, for the community to get the right product and the right message and the right way to do things, because things have changed dramatically from what they were on an old Chevy 350 20 years ago. So thank you to these two organizations and to all of you for allowing us to be a listening post for you and making the right product, the right things at the right time going forward. So my thanks to all of you.
Thank you, Chuck. Really appreciate that. Oh, thank you, Chuck Barnett and Chuck Lynch.